All right. Afternoon, everybody. Welcome to Physics Cram session number 3. Today we're taking a look at energy. First, 2 parts. We're going to do probably, again, depending on what you guys want to do, probably take the next 2 sessions, today and next Monday, and just really hammer energy out, comfortable with it. Energy is one of those super useful topics that definitely will go up on the exam. So we're going to take as much time as you guys need in order to make sure we're comfortable with energy. Okay. If at any point in time you guys have questions or concerns and stuff like that, I already see we're definitely hitting springs today, so we will definitely do that as well. But any other topics or questions you guys have, please throw them up in the chat or use that ask a question button, and we will deal with those as best we can. All right, so just a quick refresher. I know you guys are all aware, but it's Monday. It's math and English day right now. We're doing normal science stuff on Wednesdays. That'll be physics. I think we're doing the response questions from 2019, last year's exam, at 1 o'clock on Wednesday, and then rotational stuff Wednesday night. So check in and go from there. As far as the Cram sessions go, today we're doing energy. Next Monday we're doing energy. And then from then until the exam, so for the next month or so, starting next week, we're going to go Mondays and Wednesdays. So it'll be Monday, and then Wednesday, Monday, Wednesday, stuff like that. I know that conflicts a little bit with the existing physics stream, but it's kind of what we have to do here. So there's a rough idea. Energy next week, momentum the week after, SHM after that, rotational stuff on the 29th, and then that'll leave us basically 2 more weeks to really just hone in on FRQ techniques, the types of questions you're going to see for the exam, some combo problems. We're going to pull in a bunch of stuff from different units, and just general Q&A on that exam. All right. So yeah, I put the slide up again. This one you guys saw already. So it's, again, your exam is the 14th at 4 p.m. Eastern time, which is some crazy early time if you have to live in Hawaii, things like 10 in the morning. But yeah, that's the idea. 2 free response questions, 25-minute qual-quant, and a 15-minute paragraph length response. And yeah, we'll go from there. Okay, so general overview for today. I was going to hit work power, the work energy theorem, and some examples with that. Also, a reminder, the community FRQ is up on there. Let's see if I can open this up without killing everything. I can, but it's not sharing it. This one's on circular motion, orbits, energy of planets, that sort of stuff like that. In there, post your answers up by Friday, and I will go through and critique, grade, put up an answer key, where the points come from, sort of stuff like that on Friday. All right. So that being some of the questions we're dealing with springs, so I guess I'm going to jump kind of right into that idea of springs, and then as more questions come up, we'll jump around from there. So I'm going to pause the slides here and switch over to doing a notepad, and we'll just talk springs for a little bit. And load. Okay, there we go. All right, so springs. So let's first start off by doing some very basic spring stuff. We're going to grab and draw out a little spring here. So let's put a box connected to some sort of wall there. That's a terrible drawing, but it'll work. In this box, there's a mass M. Our spring has a spring constant K. And we're going to do a bunch of stuff with it. The first thing I would point out is springs are a little bit weird, but only because they're not typical. I'm sure you guys are all well aware that work is when you have a force acting over a certain distance times the angle between them. And if they're going the same direction, it's positive work. If they're going opposite directions, it's negative work, and stuff like that. Springs are where we get a little bit weird here, because the force on a spring is K times X, the spring constant times the distance we have stretched the spring. So if I were to graph this, I'd get a force and a distance, and I would get a graph that hopefully is linear. Now, in real life, not every spring will look like this. Not every spring is ideal and linear, but on the exam, every spring we're going to see should at least be linear unless they tell us otherwise. If it's an experimental question, we're trying to figure out what's wrong, sort of stuff. But what this means for us is this is not a constant force. This force changes depending on the distance. So we cannot simply say that, oh, I pull on this with this force, that's Kx, times d, I get the work done when I'm changing the energy of a spring to be Kx squared. That is not correct. Okay, 100% not right. It works great for gravitational potential energy because that doesn't change significantly with distance. It works great with kinetic energy. It does not work great with energy in a spring. Instead, here we have to remember that work is also the area of a force distance graph. So the area here is going to be a triangle. 1/2 base times height. That's 1/2 x times kx, or 1/2 kx squared. This is where we get the equation off your reference tables. That the potential energy of spring is 1/2 kx squared. And that x is just the distance we have stretched the spring from its natural length. X could be positive if we're stretching the spring out, or X could be negative, we're compressing the spring. It doesn't matter in this case. As long as X is changing, we have changed the length of the spring, we will get that energy being stored as 1/2 kx squared. So far, so good. Yep, John, pretty much exactly that's right. It's going to be 1/2 k delta x squared. On there. Now, most of the time when we talk about springs, the question is going to assume that we are at our equilibrium position, that we are at the place where, I need more space, where we can say simply that the sum of all the forces on the spring is 0. That means that, in this case, x would equal 0. So a lot of the times we're talking about delta x. More often than not, x naught is going to be 0, but maybe not always. This idea comes up a lot more if we had an experimental design question, where you'd have to measure the length of the spring to begin with, and then measure the length of the spring after you've stretched it, and then figure out the delta x part in there. For the kinds of questions that I think we're going to be seeing, it's probably not going to be a huge common thing to say, well, what is your x naught sort of stuff? We can pretty much kind of hand wave it away and say it's going to be 0. But that may not be true for every single case you can possibly think of. All right. So that being said, this is kind of the general work on a spring, 1/2 kx squared, force times distance, sort of stuff like that. The other big idea here with energy in general is that energy is conserved. That we can transfer energy from one object to another, as long as we define our systems correctly. Okay, and to help us out with that, I have a free response question somewhere in here that we're going to walk through. Here it is. This is actually the one that AP or College Board put out in the study guide, which may mean that, hey, this might be a really important thing for us to do. But this is an example of a qualitative, no, paragraph length, right? This is paragraph length response in there. So this is one that you could definitely be asked to do in there. John, as far as chemical energy, yeah, chemical energy is potential. It's stored within the chemical bonds of the chemicals. So it is stored in that form. So if you were to think about a solid liquid gas sort of scenario, a gas has more energy. No, scratch that. That's kinetic energy. Sorry. If you were thinking about like hydrogen plus oxygen makes water sort of thing, the water has energy stored in it in those HO bonds, that sort of stuff. But chemical energy, not going to show up on here, hopefully. I don't think they're going to talk about gas engines or anything like that, but who knows? All right, so I'm going to hold off on that question for a second because that's exactly what we have to do for part B of this question. So let's start off with this one here. This, again, pre-response, definitely one that I would think College Board will definitely expect us to be able to do come time for the exam in a month from now. Kind of scary. So this one, pretty straightforward. This would be a 7-point question on a normal exam, which means it's right around the 15-minute sort of chunk, which is very typical for what they're giving you as far as time goes for your paragraph response one this year. So this is kind of what we're looking at for length and depth here. All right, so we got a spring. Spring has a length L1. The unstretched length, plain or L1 right here. We are then hanging a mass on it, and we are going to go to L2. So this would be, at this point, we'd have gravity going down and the force on a spring going up, and they would be equal to each other. They would be perfectly balanced. That would be our equilibrium position, where the up force and the down force are equal to each other. And then we have L3, where we are using our hand to pull it even further, pull it beyond its natural equilibrium position, and yeah, do stuff with it. We're holding it in place. And it could be important here that this is being held in place with that hand. All right, how many forces acting on this block? All right, I see a 3. There's another 3. Okay, hopefully everybody's saying, yeah, there are 3 forces going on here. 3, 3, 3, perfect, all the 3s. So let's draw these in here. Distinct arrow starting on and pointing away from the top. Okay, so we have only gravity pulling up. Okay, this could also be FG, depending on what symbols you want to use. It doesn't really matter. Who's ever reading this exam is going to be smart enough to know that MG is FG and we're right there. We also have force on the spring pulling upwards. And we have another one downwards that's, I'm going to call it FH for the force of the hand pulling down. So 2 forces going down, 1 force going up. And they didn't give us any lines here, which is nice. And some of the previous questions, we had like a grid where we had lines and say which one's bigger or smaller or stuff like that. We don't have to worry about that this time. So it's just as long as you have those arrows going in that general direction, starting on and pointing away from the dot, we're good. Now, if this was the actual question, this would give you a grand total of 2 points for that. And how they're going to do it, they give you 1 point for drawing all 3 forces on there, and you get 1 point for not putting anything extra on. That there's no air resistance, there's no other magical force going on there in it. So basically, 1 point for getting all 3 correct ones, and 1 point for not screwing anything up, which is kind of nice. Okay, now, John, let's get back to your question here. We'll get the spring pulled downwards. We're going to let it go. And we're looking at the time during when the block is moving upwards towards the equilibrium position. So if I were to sketch this out here, we'd have our spring, we'd have our block, and we are moving upwards, and we are not yet at the equilibrium position. Okay, so we're asked to talk about a clear, coherent paragraph length response. So may also contain diagrams or equations. That could be useful to do, talking about drawing this out and explaining stuff. Why the total mechanical energy is increasing, decreasing, or constant for each of the three systems we've listed below. All right, so first things first, when we say mechanical energy, we are talking about potential energy plus kinetic energy. We are not including any friction. We are not including any sound or heat or anything like that going on. It is strictly potential energy plus kinetic energy, the total mechanical energy going on there. All right, and we have to say what's going on for each of these systems listed below. So let's take a look at system number one. System number one is the block, and that's it. So if I want to look at system one, I have my block, and my block has some forces acting on it. Right? Are any of these forces that are acting on the block caused by the block? Nope, none of them are, which means these forces, all of them are external. Come on, pick up the pen. Which means we have work going on. Okay? So the force of the spring is caused by the spring. The weight of the block is caused by gravity. That's the earth. The hand's no longer there, so we don't have to worry about it. But in this case, we have these two forces going on, and we know for a fact, because they tell us that we're moving upwards, the force on the spring is bigger than the weight. Okay, so I have an unbalanced outside force going on here. My net force is pointing up, which means I'm accelerating up, which means we are going to have our velocity be increasing. If my velocity increases, that means we are increasing our kinetic energy, which means our total energy goes up. Make sense? Okay. So with this, we want to say something along those lines. And I'll type out a paragraph for this once we're done going over all the three parts. But that's definitely something we want to say here. For system one, the total energy is increasing. What about potential energy? Well, potential energy depends on our height above the Earth, right? Potential energy is mgh. And if I don't include the Earth, it's kind of tough to measure h from the Earth. So I can't do anything with potential or gravitational potential energy because I don't have an h. I also can't do anything with potential energy in a spring because x, again, is a length, and I don't know how much that spring is stretched because I'm not including it in my system. So for the block, I can't do either kind of potential energy because we have no x's or h's to actually measure in reference to. All right. Okay, so that's system one. That is the block by itself. Energy is going up because it's getting kinetic energy because it has work being done on it. All right, system number two, the block and the spring. So now we have this interesting case going on here. We have the block and the spring going on. Here, if I want to draw this out here. So this is system two. I got my block on my spring. I got the spring still pulling up. This is an internal force caused by the block and the spring acting on each other. But gravity is an external force. It's not caused by the block or the spring. which means this force right here is unbalanced. Okay, unbalanced external force. We are going to be taking and actually losing some energy here. Okay, this unbalanced external force acting opposite the direction we are moving makes us lose velocity, which makes us have negative work, which means our total will go down. Okay, you could also think about this as we have potential energy in the spring here, and we have kinetic energy. We're getting closer to the equilibrium point. Our X is getting smaller and smaller and smaller. We are losing potential energy in our spring because our X is getting smaller. We are also losing, no, sorry, we're gaining kinetic energy. We're gaining kinetic energy, but not as much. We're not making it work perfectly equal with that. Okay, so overall, we're going to be losing some energy in this case. Right, because that one makes sense. This one's probably the hardest one to comprehend here. Yes. Okay. And then let's look at system 3. All right, system 3 was to block the spring and the earth. Now we're including everything. Right, now we've got our block with our spring and the ground. Everything's included here. We can talk about potential energy in the spring. We can talk about kinetic energy in the block. And we can talk about potential energy due to gravity. All 3 parts come into play here. If we're looking at our forces, gravity and our force in the spring, all these are internal, which means our work equals 0. Our total energy is constant. All right, so this is just illustrating how important it is to make sure that we are defining our systems carefully. Because if I ask you what's happening to the energy in this scenario, it could be going up if I look at the block. It could be going down if I look at the block of the spring. Or it could be constant if I look at the block, the spring, and the earth. And that's without getting into, did I include friction? Do I have some other thermal losses or anything like that? This is the key idea behind energy, really, is how do you define your systems so that it works out properly, so that your answer matches your system in there. All right, and now, because we promised paragraph length response, let's see if I can write something up nicely here for this. So let's see here. So there's the first chunk. Here, talking about doing the energy for E1, and it's pretty much the same stuff we just talked about. All right, for system 2, we have other stuff going on, right? You know what? I'm going to hold off doing part 2 because I think I want to come back to that part later on. Now that I think about it, there's probably an easier way to explain it if we talk about system 3 first. So for system 3, all the forces are internal, which means the system is closed. So the system 3 pretty much kind of put through the basic part of saying, hey, this is all these things are internal. It's closed, you can't gain or lose energy. E3 is equal to potential plus kinetic plus spring, and that cannot change. The last part here then, now that we've defined what E1 and E3 are, we can talk about system 2 must be equal to the kinetic plus the spring potential energy. That must also be equal to the total energy minus the potential due to gravity. Okay, so something like that. Because the potential energy due to gravity is greater, the E2 is going to be decreasing. Yeah. So it's not the force is greater; it's that the potential energy, the MGH, as that block rises up, increases. What's left over decrease. So this is where that second situation is a little bit harder to describe, because we're really talking about measuring kinetic and potential in a spring by talking about what happens to the total and the gravitation part. So kind of saying that those two things have to be equal to each other, and therefore have to, when one goes up, the other one has to go down. But because we're talking about system 2, where we're not including the Earth, we don't get to talk about potential energy being part of that system. So really, that's just energy we are losing and making disappear as we rise up. So from system 2's perspective, that energy is just going away. All right, questions on this part? I know this one was kind of tough. System 1, hopefully pretty good. System 3, hopefully pretty good. System 2 is that weird one, at least for me. And for all of you keeping score at home, this is 5 points on the exam. Where do those 5 points come from? Well, basically, they need to talk about, you need to make a claim for all 3 systems that get you a point. So whether you're right or wrong, saying that you have claims going on here that you haven't talked about any strange energies. You haven't talked about, oh, we're talking about thermal energy here, or magnetic potential energy, or anything like that. We don't have any weird sorts of energy going on, so we're good. In that case, that gets you a point. So just talking about potential kinetic, that's a point right there. Okay. You have to talk about, so talking about how system 1 goes upwards and you're gaining energy, that's a point. System 2, losing, gets you a point. System 3, being closed, gets you a point. And the 5th point here is for your logical, consistent, relevant paragraph. That you're talking about stuff that pertains to questions. You're not contradicting yourself at all here. And it's just generally correct. It's logical, it's clearly laid out, stuff like that in there. Your drawings make sense. Your equations, if you're using them, are correct. That sort of stuff like that is where your last point comes from in there. All right. Questions on this before we move on to something else? All right. Well then, let's jump back to some easy. Oh, that's not the right one. Let's jump back to another basic question, and I'll let you guys ponder this for a couple minutes, and then we'll go over this one. All right, so we get a graph, velocity versus time, moving in a straight horizontal line. Okay, reading these are super duper important here. Simply because if this was not horizontal, if we started talking about vertical stuff going on here, who knows what this would have done with this graph, how we would be able to figure this one out. Okay, we also have a single force, and they tell us that force is external. It is happening from something outside of our system. Okay, and they want us to have A, B, C, and D, ranking the work done on the box by this external force for the given intervals. All right, so which segment, A, B, C, or D, do you think has the greatest work being done on it? I've got 1 vote for B. Do we have any? 2 votes for B. All right. So let's talk about why. B is the greatest amount of work. Okay. C. C is a really good guess, and I know why you chose it. But let's talk about why B is best, or B is the biggest here, and then we'll see if we can figure out why C isn't the biggest choice. All right, so B is the biggest here. So in this case, we're looking for work, right? Work is going to be a change in the energy of the object. Now, in this case, we're talking about a horizontal object or horizontal moving object, and I don't see any springs mentioned here. So what kind of energy are we changing? Yeah, we got to be changing kinetic energy. There's no other option here. We also see that we have our velocities changing. And since kinetic energy is 1/2 mv squared, we are talking about speed changing, or velocity changing means changing kinetic energy. All right, now the question here is, in section B, our velocity is going up. That is positive work, right? Remember, delta is always going to be the final minus the initial here. So our delta for case B, our delta V, or our delta K would be 1/2 m times 6 squared minus 1/2 m times 2 squared. And 36 minus 4 is a number that happens to be a pretty big number. Okay, the key idea here is that our velocity increased. We got bigger because of this. Okay, that means our work is positive, and probably a pretty big positive too. We can make up math for this and do the math out, but that's not the point of this question per se. All right. Now let's talk about C. C definitely has the biggest change in velocity. Right, the magnitude of this change is definitely the bigger one. It went changing by 6, whereas in B we only changed by 4. But the key idea here comes from the order, that it's final minus initial. And at C, we end up going 0 at the end, which means at 15 seconds, we have no kinetic energy. We have lost all the kinetic energy we had at 10 seconds in. So while work done for B was positive, the work done for C is negative. We took away energy from our object. Does that make sense? Okay. And then A and D, what about A and D? What's going on there with my energy? Yep, there is no change whatsoever at A and D. Here our delta V is 0, which means or work A and D is 0. There's no change in energy there at all. So ranking this, B is the biggest, A and D get to share the box for second, and then poor C is at the end because that is negative work. Okay. And just to have it be official, explaining our work, this could be a paragraph, length response sort of thing. So let's get some practice writing some paragraph responses here. Work is the change in total energy It's not. It's based on the final minus initial changes. Yeah, it's not the magnitude of it. It's simply talking about the change here. And if the change is positive, we have positive work. And if the change is negative, it's negative work in that case. Okay, and there's my little paragraph blurb there. You could write this a couple different ways. I kind of just did basically how we walked through it, with positive work being in B, negative work being in C, and no work being in A and B. The other part, just to bring this out a little bit more, I know this is not part of the question, but just in case, if C, let's say, for example, we went up to B, then we dropped down immediately, and then we went like this, we went negative, and then at D, we suddenly went back up to 0, something like that. This would also be positive work, because we started off at 0 and got farther away, we gained speed, our velocity increased in the negative direction. So it's one of those that if you can say your speed, your magnitude of velocity is increasing, you have positive work being done. If you have your speed decreasing, the magnitude of velocity is decreasing, then you have negative work going on. So it doesn't matter if we're going in the positive direction or the negative direction with our velocities, as long as the change is positive, we have positive work. And as long as the change is negative, we have negative work. And if we have neither one, we don't have anything going on. All right, questions on that? Okay. John, I don't think there's a penalty for using too many sentences. The key point here is you want to be clear, you want to be concise, and you don't want to contradict yourself. So if you can say something in 5 sentences, 6, 7, sort of stuff like that, and you may be getting a little too many. It's supposed to be a paragraph, not a essay. It shouldn't be multiple paragraph sections or stuff like that. It should be, this is my idea, 4, 5, 6 sentences, somewhere in that range should be plenty for it. I've never seen somebody lose points because you've written too much, as long as what you write doesn't contradict anything and doesn't say anything wrong. Yes, and Meg, yes, that if you said A equals D in there and just a little sort of thing there, yeah, as long as you're showing somehow that they are the same value, you're fine. Yep. So both those, perfectly fine. All right. Next question then. Let's continue on our ideas with work. Okay, this one is kind of the basis for qual-quant, or at least half of it, where you have to say what's true about student A, what's wrong about student B, sort of stuff like that. So take a look at this one here, and we will see if we can figure out which student is correct, if any of them are correct. Okay. So this one, we've got 2 blocks for these to rest on a ramp. Both ramps are frictionless, so no friction going on here. they reach the same final height. Okay, so they're both going this same delta H in there. And compare their work done on the blocks by the normal force. Okay, so typically for these questions, at least when it comes time for the quant AP sort of thing, they're going to ask you, what about student A, B, C, D, F, Q, Z? What do they say that's true? So let's go through and say, okay, is anything that these students saying true? Maybe not 100% of what they're saying is true, but let's see if we can figure out what some true spots are, some truthful statements that they are saying. All right. So let's start with Anika. They say, I think the normal force doesn't do any work on either block. The force on the block is perpendicular to the ramp. Absolutely. This statement, 100% true. Okay. Normal force, by definition, must be perpendicular to the ramp. So 100% correct there. And the displacement is parallel to the ramp. Can we agree that the displacement, the change in position that they change would be parallel? I think we can, right? I think we can say that that's our X right there going through there. Yeah, that also seems to be perfectly truthful statements. So far, so good. Okay, and then she said, so the dot product's 0, and therefore it doesn't do any work. We'll get back to that in a second here. But so far, she said some pretty good truthful statements. Okay. So in work equals force times distance is de-displacement or distance. Short answer, it depends on the force we're talking about. Okay, so if we say work equals force times distance or displacement, if this is friction, we definitely want to talk about distance. If this is gravity, all I need is displacement, because gravity doesn't care how far I'm getting there. So realistically, if it's a conservative force, like gravity, like a spring, that cares about starting and stopping, we can use displacement. If it's a non-conservative force, like friction, then we need to worry about the distance we actually travel through it. So that's why D is used, and it's terrible because it can be both. And it really depends on what you're choosing to do there. Right? I think for putting everything in order to see, displacement is going to work there. One force times distance over the vector. Okay. Depending on the math you do, John. All right, so now, have you guys done calc or pre-calc or anything like that? Or am I going to talk stuff that's way, oh, no, okay. All right. Okay, so some of you guys are pre-calc. Okay, and calc. Okay, so we got a whole bunch of different options here. Here's the deal. If I say dot, parenthesis times, and cross are 3 different ways of doing math. Okay, this one is known as the dot product, and basically what that means is you take a vector, dot with a vector, you get a scalar. Multiplied normally, a vector times a vector is a vector. Not a big deal there. And then cross, a vector times a vector is another vector in there. This is what work uses. Work is a dot product. That's where they mentioned dot up in this answer here. What it basically means is we care about the parts that are parallel to each other. The cross product would be something like torque, where you care about the parts that are perpendicular to each other. So when we're talking about generic multiplication, yes, we would just multiply and we get a vector out. But the idea here behind this, and AP1 doesn't get into this a great deal because it's more of a calc-based sort of thing. If we do a dot product, we get the scalar equivalent of it out. What is the definition of dot product? off the top of my head, I cannot remember the matrix definition of it. Basically, dot, if I say work, let's get some space, work is force dot distance. That means it's the magnitude of the force vector times the magnitude of the displacement vector times the cosine of the angle between them. And since cosine is biggest at 0 or 1, or biggest at 0, we are talking about the parallel parts of them, and that is the definition of dot product. Yes, that's exactly what Anika's saying, is that the force times the distance times the cosine, the angle between them is 0. Yep, that is exactly what she's saying, just not in, you know, that way. This is also why your reference tables actually say work is FD cos theta, or FX cos theta. I forget which term they use for it, but they're putting the cos theta part in there to remind us that we need to be talking about parallel directions between the force and the displacement to make it actually have a valid work sort of thing. Okay. To put it another way, if I am taking a box and I'm pushing it at a constant speed, and my force is that way, I'm not going to be worried about it moving vertically. That doesn't matter. It doesn't do anything in there. And a horizontal force is never going to increase my potential energy. Stuff like that going on. They must be going the same direction. Which means we kind of loop back through to kind of get to the answer here. Then Anika is 100% correct. In order to do work, the force and the distance it moves must be parallel to each other, at least a parallel component, and that parallel part is true with what Anika said. All right. Let's now go through the other two and see if there's any hope that the other two are actually saying something correct as well. Okay, student B is saying work is force times displacement. Maybe it is. It's force dot displacement, or FD cos theta on there. They're saying the work I've done on block A is negative. This is 100% correct. Check the box. Okay. Gravity is pulling down on that block, and it is accelerating it. What am I saying? No, sorry. Work done on block A is not negative. Work done on block B is positive. There we go. Because if we're thinking about our ramp, we've got some component of gravity that's parallel and going over some distance there. So gravity is doing wonderful positive work on this thing. So student B is, partially right. I'm going to guess they're defining it as just the block. No, they got to do block and ramp because they're talking about normal force. So they've got to define their systems as block and ramp. Are they including the earth in there? Probably not, because they're just talking about the work done on the blocks by the normal force. So because of that, they're probably defining the system as block ramp. Meaning they can say normal force does stuff. Or maybe they may just be defining it as block on there too. So it's either block or block ramp. Either way, they're not including the earth at all in this system on there, because then you'd say that there was no work being done, et cetera, et cetera, et cetera. Okay. And Craig is also, he's got the right idea, but he's talking about distance. That force isn't pointing at all in the same direction, which means there's nothing going on here. So, and 100% correct. Student B here, Obey, has something correct, but is wrong about the displacements being positive and negative. he's thinking as being like negative x direction and positive x direction going on here. That's not what's happening in there. And Craig would be true if that force was pointed the same direction, which is not on there. Yeah, if you want to think about it, John, when you're talking about gravity doing work here, I wouldn't even worry about the length of the ramp. I would say, let's include the Earth in here. Why not? Let's say work equals the change in potential energy, which is mg delta H. Doesn't matter how I get there, as long as I got that same delta H, which I do in this case, it's going to end up being the same work done there. Yeah. If you want to, you could get into mg sine theta terms and forces and stuff like that and say, okay, so the block A has a bigger sine theta term because more of it's parallel to the ramp. That means that the force of gravity parallel to the ramp is bigger, but that's over a shorter distance. It does all come out. Craig is incorrect because he's missing the idea. If both Craig and Bobe here are both saying work is force times displacement, or force times distance, or stuff like that. That's true if the force and the displacement are parallel to each other. That's the key idea they're missing here. Otherwise, they'd be okay as long as they're defining their displacements and distances correctly. Like, Bobe is weird because he's getting that positive, negative. He's thinking of it like x horizontal, y vertical sort of stuff, where really we need to think about it as parallel to the ramp or not parallel to the ramp. Craig has it wonderful, except for the force that's actually pushing it parallel to the ramp is not the normal force, and therefore it doesn't matter at all there. If we had these cases where the force on the ramp parallel was the same for both cases, Craig would be completely correct. The distance block B travels on the ramp is bigger on the ramp. The horizontal, or sorry, the vertical displacement is not. And that's where he's getting mixed up with. So big ideas, again, going back to kind of basic principles, work must be a force times a distance that are parallel to each other, or FD cos theta. If you don't have an F, you don't have work. If you don't have a D, you don't have work. Pushing on a car that's not moving is not doing any work. And they must be in the same direction. Okay, carrying a backpack full of books while you walk at a certain speed sideways is not doing any work on those books. You're pushing up on them, but you're moving sideways. Those are not parallel directions at all. No work's being done there with that, assuming that you stop and you're changing your velocity between. Okay, that's about 8 o'clock. Any other questions on this idea before we wrap it up for tonight? All right. Then what I'm going to do is I'm going to quickly type up a response to this. This I will print out as a PDF and attach to the West slide in the slides, so you guys can have a copy of the work and stuff like that. Next week, I think we're getting you guys a preview, some energy circular motion stuff. We did that one. Some energy graphs and spring graph sort of stuff. We've got a little bit of gravity and stuff like that, doing some orbits with gravity. In there, we've got pendulums and energy changes there. More spring stuff, more spring stuff, more spring stuff, in there. All right. Well, lots of questions just popped up here. Okay, so Meg, would you say, so there's no force in this example where we had, let's get to this, there is no force that is parallel to the direction, or the normal force is not parallel, therefore it can't do any work, okay? This would be, if I wanted to write this out, this was F times D times cos of 90. Cos of 90 is 0, so there's no work being done there. John, what a question asked you to explain, can you verbally write out a calculation? Yeah, that's perfectly fine. You could also just say, like, if I'm going to write this up right now, I'm going to say something like work is force. I don't have a dot in here, times distance. This is where writing it up would be better, times the cos of the angle. Okay, so that's kind of where I'm going with that one. So you could verbally write it out, like I can work is force times distance times cos theta, or you could say W equals FD cos theta and go from there. Sure, you could definitely talk about conceptual sort of stuff. You could talk about how the blocks here are gaining, or let's think. Conceptualize. What I don't want to do is go down to, well, the blocks hit the ground going the same speed, which means they had the same amount of work done with them, which means that ... there's nothing wrong to say, conceptually speaking, and talk about it in terms of just verbally, Newton's laws or conservation of energy or stuff like that. This question is kind of tough to do it like that. The previous one we did, you could do this all very conceptually and just talk about, hey, work is the change in energy, and that's the change in kinetic energy. And kinetic energy depends on the velocity. So if your velocity increases a lot or changes, if you have positive change in velocity, you have positive work going on. If you have negative change in velocity, you have negative work going on. B has a positive change in work, therefore, or positive change in velocity, therefore it's the biggest work. A and D have no change in velocity, which means they have no work, and that sort of stuff. So you can do it conceptually. What you don't want to get into doing is doing it just using anecdotes and stuff like that. So saying, like, if I were to do this in the classroom, the blocks would hit the ground with the same velocity. Yes, but you didn't actually explain any of the physics behind why that happens in there. So I guess whenever it's asking you to explain something, you want to do something where you can relate it back to, this is a scientific concept that we're working with. And if you got the scientific concept, we're good. Yes, I would almost always blend it unless they're telling you specifically, like, don't use math. And if they're telling you don't use math, then you're going to refer to Newton's laws, conservation laws, stuff like that, and kind of verbally spill it out. When you're told to derive an expression, can you annotate our derivation? Sure, I don't see why not. Most of the time when you're going to be deriving stuff, though, it's going to be, here are the terms you're going to use, or you've already defined the terms you're going to use, and then do stuff with it. Like, for example, like in this case here, we're going to be probably deriving an expression next week. We're going to be talking about things like H and R. are going to be the two things that are going to end up in our derivation. Maybe G because it's a constant and understood for mass. There shouldn't be a ton that you need to explain what that derivation means. But definitely if you want to put a few little tidbits in here, like here, we're going to use Newton's laws, or here, we're looking at the system of block 1, or here, we're looking at ... That sort of stuff is fine. But really for derived, they want to see the math. They don't want to see the other written portion of it in there. Justify, use them both. Derive, just the math. Explain, probably more words, but you got choices in there as well. In fact, what I'll do is I will look up on College Board. They've got a pretty nice example of what those terms mean here. Let's see if I can find it quick here. Let's see. AP exam words. That's not exactly the right site. Okay. Yeah, so is my CD. AP Physics 1 CD. And load and download. We'll see if this actually comes up quick here. Let's equations. That's not useful. Okay, there we go. This is what I want to see. Can I snip this quick? All right, so remind me, I will definitely throw this in the beginning of next classes or next time too. But this is where we're looking at for this sort of stuff. Where's my paper? Give me a new page, paste this in. Okay, so this is kind of where it's talking about it, and this may not be the best thing to show here. But for example, derive, they really want to see math. They want to see mathematical steps coming to an answer. Explain. Information, just simply how or why a relationship occurs using evidence and or reasoning. Justify it, that's a bit more in depth. So why does this actually support your claim or match up and stuff like that in there. So there's kind of the terms you're going to be seeing in there. If I were to make a note sheet for the exam, what would I put on it? Oh, goodness. I guess the first thing is I'd have to make sure that, number one, I would make sure we know our conservation laws. Know conservation of energy and examples of when it applies, when it doesn't apply, kind of like the systems problem we just did already. I would definitely have maybe a worked out example of something dealing with like potential into kinetic or springs or stuff like that. It's tough for me to think about it because mostly what I would say is know your reference tables, know when to apply those equations, and then everything else that I would put on a note sheet for the exam would just be things like, well, maybe some of these examples of what does it mean to justify, what does it mean to derive, just so those you're clear on what those mean, and then maybe like a velocity time graph. Sort of thing, and make notes. The area is the displacement, the slope is the acceleration. A force time graph, the area is the change of momentum. Force distance graph, the area is the work done. Rotational motion, maybe a couple like sample, this is how you find torque, this is how you find angular acceleration. Maybe here's an example for one of the old practice questions we go through. Here's how you would solve that sort of stuff like that. It's one of those, because this is so conceptual, it's tough to say just write down all these definitions, because definitions aren't going to help you a ton. It's going to be a lot more of, can you apply this concept? Do you know how to use this? Do you know when this applies, when this doesn't, sort of thing. So that's probably not super helpful because it's probably not. But yeah, basically what I have my kids do a lot is we'll just go through a practice exam. And I wish I could show you one, but I can't. Your teacher, if you email them, could probably set you up something on AP Classroom or something like that. And we basically just go through with, okay, what is this question talking about? What are the topics for this question? Is this energy? Is this forces? Is this momentum? And get really good at picking out, okay, this is the type of things I could use on this question. And then from there, we can go to the reference tables and say, okay, here are the equations for that topic. And then plug and chug from there, sort of thing. But I found a lot of times where my kids struggle is not in doing the math. It's not in explaining what's going on. It's making that first step of, what the heck am I supposed to do in this question? Is this projectile motion? Okay, if it is, x equals x naught plus v naught t, you're running there. Are we talking about forces? F equals ma, good place to start. Are we moving in circles? Are we rolling? Are we crashing? Are we penduluming back and forth? And really get good at matching those things up for it. Especially when we only have a few questions on this exam coming up. That's going to be a major skill. Just what topic are we going to get onto? And then once you've got the topic, then jump to that notes page with, oh, here's a simple problem dealing with blank. I can use that sort of thing. All right, no problem. What we might do is when it comes time to when we get close to the exam, like maybe the week before or something like that, we could take one of these sessions and just kind of go through. Let's just cram everything into one. Let's make a cheat sheet and go from there. I'll ponder that question, but that could be a really good option for it. So, yeah. All right. So I will, I'll leave myself a note, and if you guys can remind me, shoot me an email or something like that too, and we'll go from there. And I'll definitely try to work that into our kind of pre-cramming cram sessions. All right. Have a great night, guys, and I will see you hopefully Wednesday afternoon. Do some FRQs, or if not, next Monday for continuing on energy. All right. Have a great night, guys.